In this lecture, we illustrate the fourth-order Runge Kutta method when numerically solving an initial value problem. The initial value problem, or IVP, is given by the differential equation y prime of x equals x squared plus x times y of x, with y of 0 equal to 1.2. With the help of the software Mathematica, we are going to find a numerical solution to the IVP on the interval from x equals 0 to x equals 1.5. Since the problem does not prescribe the subinterval length or step size, we will choose the step sizes, or equivalently, we will choose the number of subintervals and find a numerical solution for each number of subintervals. Suppose the general IVP is given by y prime equals f of xy, with the initial condition that y of a equals alpha. We set x sub 0 equal to a, and y sub 0 equal to alpha. Let n be the number of subintervals partitioning the interval from x equals a to x equals b. Then h equals b minus a divided by n, so that we have a uniform partition. We also have x sub I plus 1 equals x sub I plus h. Then a recursion for the fourth-order Runge Kutta method is given by y sub I plus 1 equals y sub I, plus the sum of k sub 1, 2k sub 2, 2k sub 3, and k sub 4, divided by 6. K sub 1, K sub 2, K sub 3, and K sub 4 are given by these equations. The index I goes from 0 to n minus 1. If y has continuous derivatives of up to order 5, then the local error for the method is of order 5. The global error, on the other hand, is of order 4. We start the Mathematica code by defining y prime. Y prime is f of xy, and f of xy equals x squared plus x times y. The left endpoint a is 0. The right endpoint b is 1.5. The initial value of y, or y of 0, is alpha. Alpha is 1.2. For the first trial, we set the number n of subintervals equal to 15. H is equal to b minus a all over n. X sub 0 equals a. Y sub 0 equals alpha. For the recursion, we apply a do loop inside which we have a list of commands. The first command is for x sub I plus 1. Then we define the k sub j's. K sub 1 equals h times f applied to x sub I and y sub I. K sub 2 equals h times f applied this time to x sub I plus half a step size, and to y sub I plus half of k sub 1. K sub 3 equals h times f applied to x sub I plus half a step size, and to y sub I plus half of k sub 2. K sub 4 equals h times f applied to x sub I plus h, or x sub I plus 1, and to y sub I plus k sub 3. Now we have the recursion for the y values. Y sub I plus 1 equals y sub I plus the sum of k sub 1, 2k sub 2, 2k sub 3, and k sub 4 divided by 6. The counter I goes from 0 to n minus 1 if the last pair of coordinates is to be x sub n and y sub n. In order to view the result, we use the table command for the coordinates x sub I and y sub I, with I going from 0 to n. We evaluate the code. These are the coordinates of the points on the approximate solution of the IVP for n equals 15. We increase the value of n to 1500. Instead of showing the coordinates of all the points, which will be too many to fit on screen, we will show the last 10 points. So instead of letting I go from 0 to n, we let I go from n minus 9 to n. In addition, and just out of curiosity, we apply the timing command of Mathematica to see how quickly or how long it takes to determine all the points as the software executes the do loop. So after the do loop, we type /timing, and we execute the code. This is how long it took in seconds for the software to determine all the points. The word null appears because the do loop command has no on-screen output. Let's increase the number of points to 150,000 so that each step size is 10 raised to the minus 5 power. We execute the code. It took this much longer to determine all the points. This is the approximation of y of 1.5, which up to 6 significant digits matches the one we obtained for n equals 1500. We now plot the points for n equals 150,000. We no longer need the timing command. Since we will be plotting all the points, I has to go from 0 to n within the table command. We call the set of points points. We type a semicolon after the table command so as not to flood the screen with the coordinates of all the points. We apply the list plot command. We list plot points. We execute the code. This is the plot of the points for the approximate solution when n equals 150,000. As an exercise for the viewer can try to plot the points for different values of n and superimpose the different plots for comparison.